So pressure and temperature. We're going to isolate these two variables here and take a look at what happens as we have some sort of change in this system, right? And so remember, with system, we said it's just those conditions that we're looking at as far as our gases go, right? So, we're going to have what we think of as our initial system, and you're going to notice that I'm doing something a little bit different here than I've done with the other diagrams, illustrations that I've done. Here I've sort of colored this in, right? And I'm going to do the same again. So obviously the first one I drew was what we call our initial condition, right? Condition 1, the starting condition, blah, 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 blah. So here I've covered this in. These are both the same container. We assumed this is initially how everything was conditioned, right? How it began. And then this is the result of any change, right? This is the change condition. All right. So go ahead and put condition. Why not? And we've been sort of following this concept of, I've been using 10 like in all my videos. It's just an easy number to work with. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm just drawing them scattered about, right? Because they're just there. They're just doing their thing, right? So I'm drawing this dark. And the reason why is, on the other videos you'll notice in what we do in class, I'll draw a beaker and I'll sort of draw it looking a little something like this, right? And what that's assuming is the opening into the beaker. So here I'm drawing these closed because what I'm doing is assuming what's called a closed system. So think of the concept of open and closed. If something is open, that means that things can go in, and if wherever that opening is, things can go out. Well, conversely, if it's closed, then you make an assumption that whatever is in there cannot escape, and whatever is outside of that cannot enter. All right, and so that's the basic concept of an open and a closed system. All right, and so for these purposes, since we're looking at pressure and temperature, we want to assume that nothing can escape. And the reason why we want to do that is because we're assuming some sort of constant condition, okay? Constant condition. And so, the number of particles, we've kept the number of particles at some sort of constant, assuming X amount of moles of it, right? And then we want to also assume that the volume is constant. And so however much gas is there, none of that gas is escaping and no other gases are coming in to the container that would be interacting with what's already there, right? So we're going to keep this number 10 as is, so there's no changes, right? Now let's think about this right here. So we're looking at pressure and temperature. All right, so there's going to be a certain pressure here, right? And then there's going to be a certain pressure here, and then there will be some temperature, and then there will be some temperature. All right, so we already know that that's going to be the case, right? So I'm just going to go ahead and put those variables down. So now let's think about this. We can already see that obviously this is the initial condition, so we can label these P1, T1. We can label these P2, T2. Okay. So now, if we were to assume something with our initial condition, let's assume that the temperature, it's at some temperature. It's at temperature X. We don't need a number. It's just whatever that temperature is. Okay. Then whatever the temperature is, there's going to be the gases, as they move around, are going to be exerting pressure on each other as they collide. Right, so you'll go back to the whole concept of kinetic theory of matter. This matter is in motion, it's moving, it's doing its thing, it's hitting, they're colliding and hitting each other, but those particles are also, as they hit each other and they come close to each other and they repel each other, they're also hitting the container, the size of the container. Well, the container is then pushing back on it. So there's this constant movement of gases. And every single interaction generates X amount of pressure, a certain amount of force. Okay? And so if right here we have the temperature, right? So we're just sort of assuming we're just assuming that the temperature is at is it in some condition, and then the pressure is whatever the pressure is. Now all of a sudden we think, wait a minute, what happens if we were to increase the temperature? Well, what would happen to the pressure? Well, none of the particles can escape. If the temperature increases, then what you're doing is increasing molecular motion. If you're increasing molecular motion, then that means those particles begin to move faster. If they're moving faster, they accelerate faster. That means they collide against each other at a faster rate. They collide against the outside of the container at a faster rate, or the top part, bottom part of the container, wherever. And that constant motion back and forth, that constant input of energy from an increase in temperature creates and generates a greater amount of motion, which means that there's going to be an increase in the pressure. It just sort of makes sense. And so what we do is we realize that these gases have to be spread out further apart. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 10 on there. So arrows are kind of like in math class, like a vector. And so, like a ray, right? If you've got it, the value of it, the magnitude of it, is usually represented by the length of the size of it. And so if you draw one arrow shorter than another, you assume the shorter one has less value as far as a magnitude goes, and the larger one has greater. And so since we realize that there's a greater amount of pressure here, then when we draw this, we want to draw the arrow longer than it was here, because in the change condition there is a greater amount of pressure that is being exerted. Okay, and so I'll take this one and draw it going this way to show that it's pushing out, right? Pushing outward. So that's what we need to get out of this. And that kind of makes sense. You already kind of know this. For instance, you take an aerosol can, right? It's in a closed system. There's gases in there, like hairspray or something like that. There's gases in there, and they're trapped. They're in a closed system. And if you look at this containers, it has warnings on there that says store at a certain temperature. Well, the reason why is when you change that temperature, there'll be a temperature range. It'll say store between this temperature and this temperature. Well, the reason for that is if it gets if the temperature increases too much, you already kind of know, wait a minute, there'll be too much pressure on the inside. That thing could pop and explode, and that creates a hazard. All right, so you already intuitively kind of know this, and this is basically a loose interpretation of a Gay-Lussac's law, which looks at the relationship between pressure and temperature. Okay, so now we can sort of begin to quantify this a little bit, right? So we're going to do what we've done in all of our other videos. All right, so we've got pressure and temperature. Now, pressure can be measured in multiple units. Multiple units. The basic general one is, like we've talked about in a previous unit, which is atmospheres, ATM. So it's just a standard. So at sea level we're at an average of what we define as 1 atmosphere, right? And then temperature has to be converted to Kelvin. Okay, it has to be converted to Kelvin. That's a capital K, not lowercase k. All right. So now, speaking of K, let's also take a look at what we've talked about. We can see here that this relationship, we can glean from this that pressure is proportional to temperature, not the inverse of it like we've had in other examples of variables. There's a direct relationship between this one increases, this one increases. So that means that if this one decreases, this one also has to decrease, which means that we now know that pressure is equal to temperature times some sort of constant variable, right? And so we would get something that looks sort of like that. It looks like a very direct, I mean, we can see here from our understanding of basic concepts that we get something that is very linear, and we would get a curve that would resemble something like this on a graph. Now, if we go back to this, understanding k being our constant, whatever we're holding constant in this condition, as we've seen before, then k would have to be equal to, sorry about that, pressure divided by temperature. So that means this initial, there's the pressure over temperature at some constant. And that means at some constant you have here this pressure over this temperature, right? And so now remember, we sort of bring those two variables together to the same. If k equals this and k equals this also, then those two things must equal each other, right? And so it just goes back to a very basic algebraic concept that we've been taught for years, right? That always seems to work itself out. So we've got P1 over T1 equals P2 over T2. And this right here is the form of Gay-Lussac's law that we can use to show our initial condition as it changes in that system. So we can look at a change in temperature, a change in pressure, and we can see what the effects will be. And this is sort of the way that is the basics on how we do that. If think about how this could be applied in, we've already talked about like aerosol cans. Well, I mean, gases are fluid, so wherever you have a gas line, right? Those gas lines are made out of certain materials, and they're going to be subjected to temperature, both the internal temperature that is generated from the dynamics of the gas going through the line, right? And the effects of the temperature that's the ambient temperature, whatever is around that system, right? So think about a propane tank. You have to hook up a line to it, right? Well, those things are made up of certain materials. And so the gas that is compressed inside that propane tank, when you open the valve, those gases are released through there. Well, all those materials have to be made out of things that, one, won't interact with the gas and degrade in a very short amount of time. They'll hold up to that. And two, they also have to be able to withstand varying temperature changes. You know, people hook up these gas lines. They're used in colder months. They're used in hotter months, right? And there'll be warning signs saying, you know, don't store this directly in sunlight for, you know, extended periods of time. And so we already kind of instinctually understand Gay-Lussac's law that we're going to want to make sure that the gas is trapped inside that closed container don't get superheated, because they're going to create a whole lot of pressure that's going to push out on that, and that could be bad. All right, so you're already very familiar with this. Let's go ahead and let's do a practice problem. So let's just mathematically sort of work this out a little bit. So we've got our system. Again, just some container, and then that container obviously is going to undergo some sort of change, right? And so we've got our initial condition, and then we have our changed condition. All right. Our initial, and we have our changed condition. Once again, we'll go with the whole 10 thing, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then, so obviously we know we're going to have a P1, T1, we're going to have a P2, and we're going to have a T2. So we can already begin to set up our equation. And then we just have to look for what conditions are happening here. So I just made up a problem off the top of my head. So let's assume that this container is initially submitted to half of an atmosphere, 0.5 atm. All right, and sorry about that. I'm not remaking the videos just for little things like that. Got to see the time and maybe a little bit of weather. So let's just assume the temperature is somewhere around room temperature, which is approximately about 20 degrees Celsius, right? And then the temperature is increased quite a bit. Let's just say the temperature is increased to, say, around 40 degrees Celsius. So, to give you, if I know Celsius is something that people are not necessarily intimately familiar with, unless you work with it all the time. But remember, the human body, 37 degrees Celsius is the average human body temperature, right? So around 98.6, and most people's body temperatures tend to be a little less than that. But 98.6 Fahrenheit is equivalent to 37 degrees Celsius. So 40 degrees Celsius gives you an idea of around how hot it is. So in Fahrenheit, 40 degrees Celsius, it's a little above 100 degrees Celsius, Fahrenheit, right? So it gives you kind of an idea of what's happening here. So we can see that the question is what would the change in pressure be if that were to increase, right? And so step one is figure this out. Now you should already be able to look at this and understanding our relationship here that we've discussed, right? As the temperature is increased, so our final answer should be a pressure that is higher than what we originally started with. You should already be keeping that in mind. Too often I see people turn in answers where it's the exact reverse, but it's a direct relationship. So if you see an increase in temperature, you should see an increase in pressure. If you see a decrease in temperature, you should see a decrease in pressure, right? It just makes sense. It's increase, increase, decrease, decrease, all right? So we're solving for P2. So make our math teachers proud, and we want to rearrange this equation to solve for the missing variable, right? And so now we get a new form of this equation, which is P2 equals P1 T2 over T1, okay? Hopefully you know what we need to do next. When we're dealing with temperature, we have to add 273.15 and for our Kelvin units, right? So everywhere where we have temperature, we're going to have to add that in. So let's see. We see pressure P1 we see is 0.5 atmospheres times T2 is 40 plus 273.15. Once we add those two together, we will then bring in our unit Kelvin. All right. And then T1 was 20 plus 273.15. Now, I just need to make a note. Oftentimes, in practice problems that you'll find online, that you'll find in textbooks, that we'll do in class, we can drop the 0.15, and we can still get a pretty good idea of where we would be at. Matter of fact, I'll mathematically do this one with both the 0.15 and without it, and we'll see the differences in the numbers. I'm just giving you a heads up on that. In lab, you would definitely want to use the 0.15 since a lot of our lab work depends on on precision and accuracy, right? And so what we have right here is we've got 0.5 atmospheres, right? And then we've got 40 plus 273 273.15, right? So now that gives us 313.15. Now we have Kelvin. And then 273 plus 20, so that would be what? 293.15, and again, that's Kelvin. All right. So remember, like units, it's all about those units. I know I say that all the time, but I cannot emphasize it enough. You'll just know when you're right or wrong based on units. If your units don't work out right, if your units don't go away that you need gone, you're doing something wrong. Just stop. Just figure it out right there and get that thing fixed. Don't do more work than you have to. You're not doing extra work by writing units. You're making sure you don't have to ask questions at the end of, am I right or wrong, and then sit there wondering. So we've got 313.15 times 0.5, right? and then divided by 293.15, we get 0.53411 and a bunch of other numbers. There's some 2's and finally a 9, right? And then that would just be atmospheres, which is good. We're solving for P2, so we should have atmosphere. And so, you know, our answer about 0.53 atmospheres, 0.534 atmospheres. Depends on how many significant digits you want to use. We had 0.5 atmospheres. We could think of that as 0.50, 2 significant digits, so 0.53. Because we don't want to just say 0.5 atmospheres. So we really need to be thinking of this as 0.50, as this is 0.50 for 2 sig figs, because if we only use 1 sig fig, we'd have 0.5 as an answer, and we're saying the pressure didn't change, which that doesn't make any sense. So here's where you realize I'm really going back and inserting a 0 here. We could go 0.500, and then the final answer would be 0.534 atmospheres. And so again, the more significant digits you have, the more precise and accurate your answers are. Okay. So let's do this again real quick. I'm curious. So let's see, if we went 40 plus 273, now that's times 0.5. So you should see that you'll get 156.5. Okay. So what I've done is I'm redoing the top without the 0.15. I'm just assuming it's not there. Divided by, we've got 20 plus 273, we get, if we do it this way, we get 0.53412, excuse me, my apologies. I'm not going to redo this video. I'm human. I had to sneeze. You can see that that 0.5, it really didn't make that much of a difference. So oftentimes when these problems are done, we just use 273. We ignore the 0.15 and we go about our business, because you can see it's not until you're 5 decimal places, 5 significant digits out, that this 1 becomes a 2, right? Where it is important is like in industry, things of that nature, things you take for granted. You go to the store and buy stuff all the time, and there's a trust system. We just assume that the people who are making the products and then selling them to vendors who sell them to us, that they're doing the math correctly and they're accounting for everything. They're accounting for all these crazy changes, and so that's already done for us. We just trust in the system that it works. But now you have a better understanding of of how valuable this 0.15 is, when it's valuable to use, when it doesn't really make a difference on how to use it. Okay, knowledge is power. We're good. We got this. So you can see that we had an increase, and so it follows the relationship here with Gay-Lussac's law. All right, there we go. Hope that helped. Keep watching the videos, do some practice problems. Be sure to contact me if you have any questions. I'll be sure to answer them for you. Hope this helped. Bye.